Let us start our class today. In the last class, we have finished the theories of bending of the beam itself. Now, you know that we have got few discussion on the stress concentration for the last class, but I have stopped that class and came to here because certain equations of bending moments are required to know in order to do the work here. Now, let us start that chapter again from where we have stopped. And those, what is stress concentration, other things, it is very clear to you, and that is rather simple. But now we have to go through what is the effect of stress concentration in different type of applications, like say, plate with a circular hole itself. Here, what we see is here we are talking about the circular hole itself. This is the definition is circular hole itself. Now, here we saw a plate width of say width W and thickness T with a small circular hole of radius C itself. The plate is subjected to a tensile stress sigma at a distance far removed from the hole itself. The plate is subject to tensile stress sigma here. What is visible? This is sigma, and here it's at a distance far removed from the hole itself, because the hole is rather small in comparison to the size of the width W itself. So effect of the hole, the stress concentration effect, you can ignore to a certain extent. Now, this problem, an approximate solution can be obtained using the energy method of this type of problem, and method and the curved beam theory itself already we have discussed. Now, for this, we are considering a large hole here. Initially, actual hole is this one. This is comparatively small hole here. But to begin with our discussion, we consider a large hole like here, which is drawn concentric with the hole, and concentric means it's of the same center of the small hole, and exactly at the center of the thickness of the plate, and having a radius b itself. This hole has a radius small b, it's a small b. So what we have, the width of the plate is W, radius of this small hole is T, and radius of this big imaginary hole is equal to B itself. This cycle is also again that theory far removed from the small actual hole. So you can assume that stress condition around the circumference of the hole is not affected by the presence of the small hole itself. And this small hole we are ignoring at this present moment. Now what we are doing now? Next, we have to understand the stress distribution along the circumference of this particular big hole itself. So we want to know the stress distribution here, because the stress distribution among our actual small is rather small. It is difficult to understand. So we have to go for the imaginary hole and starts calculating the stress distribution accordingly. Now, here what we have drawn here is that this circle showing all these external holes, which is equal to sigma itself, and shown as an arrow in all the outside direction here, and all the arrows are vertical. Half of them is vertically upward, and half of them is vertically downward itself. Now, let us consider a triangle Let us consider a triangular plane PQ. Now, at the point D, this is the point D itself, and what we are doing is we are having a tangent D like this, which is tangent to the circle here and normal to the radius here. Radius is starting from D, of course, of the whole center of the whole axle, of course, yes. That 12.5C, this is this figure. We are taking this value PQ, and which is the tangent at the point D on this imaginary circle itself. So this is there. What is there? This radius is subtending an angle theta here at this with the horizontal itself. So if we draw this line PQ further and make it here you have the angle here will be equal to 90 degrees minus phi itself. Now we know the width of this portion AB is equal to the width of the our street itself. So this is equal to W itself. So we are like to find out what is the length of this portion PQ, which is the hypotenuse of this triangular hole with base equal to WB, AB or equal to W itself. That is W. So hypotenuse will be equal to W divided by W by sin phi itself, or W by sin phi, or W by cos 90 degree minus phi. Okay, so this is exactly the length of this line PQ is W sin phi, and the area of this section is W, and thickness you have multiplied by the thickness itself. So it is that W into T divided by sin phi itself. Well, W is the width of the original hole itself, original strip itself. Now the stress across this diagonal PQ, this is the diagonal PQ, is sigma dash is given by sigma WT divided by the area of this particular straight line itself. So that will be equal to W into T divided by sin phi, because the area of this triangle PQ, area of PQ is equal to WT divided by sin phi itself. So we can reduce this. We can after simplification we can know the the stress along the leg PQ is given by sigma sin phi itself. This distribution here is the function of PQ. Means this stress distribution is the function of this angle phi, and this phi can define at any position, and with by drawing when this radius with different type of phi different value of the phi drawn like this, and we can just have the tangent of this line, and with this tangent will be given by this load shared by this tangent is given by W sigma multiplied by sin phi. But sigma is the original stress acting for both the ends of the strip itself. Now let us consider a thick circular ring. Actually, what we have done with our we have a strip of certain width and thickness and have a small hole inside it, whose diameter is known to us, and we have made one imaginary circle like this, whose diameter is equal to P, surrounding this small circle, and we are saying that we are ignoring the effect of this inner circle because it is too small. Now we think that instead of the plate itself, we have the thick circular ring of outer radius equal to of thickness equal to P, and inner radius is equal to the original inner radius of this hole, and outer radius is the radius of the imaginary cycle D itself, and it is now subjected to a load sigma sin phi along the periphery as in figure here. What we what we do here, here we are drawing a diameter from the center O here, this is O, and which intersects the external circle at here. And if we draw a triangle, this radius vector has a inclination equal to phi, and so this any stress acting over this particular tangent itself is equal to sigma sine phi, where phi is equal to the phi intended by the phi of the intended angle of the diameter itself. Now, what we are going to do the next is consider a quadrant. Let us consider a quadrant from here itself. Quadrant means 1/4 of this particular round tablet. 1/4 of it means from one segment from here to here, and this segment we are considering here. Here we are considering the segment of MM from a cross-sectional. We made a cross-sectional section from MM, and we have a quadrant M, N, and S. Now, the reactive force along MM consists of a longitudinal force here. This is the longitudinal force, and a moment m0, which points the dot, which maintains the slope, there as slope there as 0. So what we have here in this tangent, in this quadrant of a circle, we have these external forces here, and which is at different points given by sigma sine phi, and where phi is the integral angle. So all these different points can be available by sigma sine phi if we know the external force and if we know the sigma itself. Now, on this line Mn itself, to maintain the equilibrium, we know as we are having a free body diagram of this quadrant. So to maintain the theory of free body diagram, we have to make imaginary forces, which is creating exactly the equilibrium with the actual external force here. Here the imaginary forces are equal to 90 N0, and if it is acting downwards, it is exactly opposite to the external force in order to balance this effect, and M0 is acting clockwise in order to have the clockwise moments created by this particular external forces at different portion itself. Now we have to find out the value of N0 and M0 one by one itself. The value of N0 is now obtained. We can integrate how we can integrate sigma sine phi from 0 to pi by 2. This is the from here to here the angle is 90 degrees. This means pi by 2, which means we can integrate from 0 to pi by 2. We are to know the value of the maximum stress N0, which is exactly balanced by the force over the circumference of this portion of the circle itself. How we can do this? Force over the circumference is sigma sine phi. It's and thickness phi, and multiplied by the area is equal to B, which is the radius of this external circle from here to here. That is equal to B, and multiplied by thickness T, which is the thickness of this portion of this string, and which is again multiplied by T phi, which is any elemental thickness phi, elemental area phi, which is intended angle phi at the center here. So if we put this angle and make the integration and put the end portion of the integration like this portion will be sigma bt into cos phi multiplied by 0 to pi by 2. You know, cos 90 degree is equal cos 90 degrees is equal to 0, and cos 0 degrees is equal to 1 itself. So sigma N0 is minus sigma m sigma bt itself, minus sigma bt itself, which is showing that it is exactly opposite to the inclination of the value of the inclination sigma itself. Now, the strain energy method, as we have discussed earlier, is used to obtain M0, means the total torque which is created here. Because only if you know the torque here, only then you can use the energy of strain energy equation itself. So we have to find out what are the different torques acting over this portion of the section. Now, here, this same I mean, this uh, same ring with a central hole, we have plotted here. For the same coordinate itself, full coordinate is plotted separately, and we are thinking of a angle theta, which is for we intended from the horizontal line MN and up to a radius shown by up to a particular radius. Here, rho zero is given by the diameter from the center of the centroidal axis, and we have to find out what is the diameter R0 of the neutral axis over this ring itself. That we'll go through one after another. Now, first of all, the external moment, this imaginary moment M0 is equal to M0 itself. Next, we have a moment coming out from the force M0 itself. Now, M0 is acting exactly opposite to M0, so we are putting it negative here. M0 multiplied by the distance of this force from the center itself. Well, what is B plus C is the distance of it is the rho zero is equal to B plus C. Rho zero is the B plus C equal to 0, where rho zero is the distance of centroidal axis. How you are getting this from B plus 0? B is the width, and if we subtract this, B is the radius of this external angle. That is, if we subtract the radius of the internal angle, inner radius C, and we divide by 2, and we'll get the distance exactly half here. And we know and if we have to add C here, the radius of the C. So actually we have to know, because we have to calculate this B minus C by 2 is the length of is the distance of the central line from this particular point itself, which is the point of intersection of the MN this line MN with the circumference of the inner hole itself. And we have to find out the distance of radius of curvature from the center of the hole, center of our curvature. So we have to add with this thing the value of the radius again, radius of the inner hole again. So this means B plus C by 2. This is equal to B plus C by 2. C by 2 is the equal to the area is the length of rho zero, or distance of your center of gravity from the center of rotation itself, center of curvature itself. So it is rho zero, or B plus C by 2 minus rho zero cos phi is given by N0. It's given by N0 B plus C minus multiplied by 1 minus C0, because this rho zero is of course B plus C divided by 2. So we can take it common as 1 minus and make it 1 B plus C by 2 minus 1 minus cos theta itself. Next, it comes the moment of the distributed forces. What will be the moment of the distributed forces? First, we have to find out what is the moment of the distributed forces. Sigma into sigma sine phi is the moment of sigma sine phi is the stress on all the radius itself. Sorry. Sigma into sine phi is the stress of over all the different forces. Say here, what it will be, it is the angle, it is the radius here, which is dependent by an angle theta, and the forces acting over this area is always all the forces acting over this area is given by sigma into sine theta, as we have already reduced, multiplied by the thickness T and multiplied by the width B itself. So total force at this moment is given by sigma T sine phi into B itself. That should be multiplied by a elemental angle delta phi, d phi, which is acting at the end itself. Next we have to do, this is d cos theta exactly. It is d cos theta, and that means the radius, if the radius here is d, then the height here should be like this. This length will be d cos theta itself. And b plus c by 2 cos into cos minus b plus 3 by 2 into cos theta is the distance from the axis of the quadrant, rho 0. As we are understanding that we are taking the moment, taking all the moments along the centroidal axis, here b plus c divided by 2 is the radius of the distance of this point on the surface from the C0 minus distance of the center of gravity, which is b plus c by 2 into both are multiplied by cos theta itself. Here b minus 3 b cos phi, it is the elemental area here. This is the phi multiplied minus, actually this is b cos phi, where we consider this element here. So the distance of this point from the center of gravity, distance of this point from the centroid of this round place is given by b cos theta minus b plus c divided by 2 cos theta itself. Now, what you will do? Now you have to simplify it to a certain extent. We brought this d by 3 phi here, and sine phi is brought here in b cos phi, b plus c cos theta itself. Again, we have to now we have to integrate it between the range 0 to theta. So what we are doing is we have to calculate the force moment of the forces acting from here to here itself, from this position to up to the point, up to this point, which is subtended by an angle theta itself. So from 0 to theta itself, so from so b cos phi is the distance of this point of our consideration here, minus b plus c by 2 cos theta itself. So you simplify a bit here, and next we are making sine phi multiplied by b cos phi, and b plus c by 2 cos theta multiplied by sine phi itself. So after integration, this portion will become half b sine square phi, and right portion become plus b plus c divided by 2 cos theta cos phi itself. Here we have to put the limit of boundary condition from 0 to 5. So it becomes minus is half b sine square theta plus b plus c by 2 cos theta minus 1. How you are getting it? You know that cos theta after the integration will become, this is actually this is sine phi multiplied by cos theta, and sine phi after integration will become cos phi, and cos phi cos theta is there. And here we will have sine phi multiplied by cos phi like this, cos phi. If we multiply the 2 and again multiplied by half, it will become half 2 sine 2 phi. And if we integrate, it will become half multiplied by 2, and this will, no, sorry, this it will go out. 2 multiplied by sin phi. This 2 will come out, and this will be integration is equal to cos 2 theta, cos 2 phi itself. And it can further reduce half into, or this half can be reduced 1 minus 2 sin square phi. This is the value of integration itself. And if we integrate there, we will get, and this b will be outside, and that is b is outside, here will b is there. And if we integrate, this thing will equal to theta. First, when you put the theta, it will become 1 minus 2 sin square theta. And next boundary constant, we have 1 minus 1 minus 1 minus 2 sin square minus 1 minus 1, it will be there. So this minus 1 plus 1 will cut together, will get d by 2 half sin square theta by 2 itself. Now, thus we get the moment due to the discharge force itself. The total moment we have to add together, m0 is like this, and we have to minus the value of m as well as the value of this moment due to n. We have to minus. We are subtracting this because it is opposite direction and represented by minus n0 itself. And here we are having the moment due to this distributed force, which we are again adding here from here to here itself. And again, further simplification of this thing will get if we replace this is as sin square theta. This is unbeaten 1 minus cos theta. Will further replacement if we divide it into 1 minus cos 2 minus cos square theta and subtract the 2 here, we'll get cos square theta plus 1, cos square theta minus 1, and from here it will take one of them and it will be reduced like this. And this side remains as it is. So from here we are taking this common and taking this common, and thus we get 1 minus cos theta and thus 1 plus cos theta itself. And this thing remains same, and this becomes 1 minus cos square theta is equal to sin square theta. This has become sin square theta because 1 minus cos square theta cos square theta is equal to sin square theta. And if we simplify this a bit further, we will get m0 half sigma bt c, bt into c sin square theta itself. Now, what we have here is the vertical load from other portion of this triangle itself is other portion of this quadrant. We are having the normal force n here, with normal force n acting here. This is normal force, and normal force n dash cos theta is acting over this here, which is the base of this triangle with the angle theta itself. This is theta and this is theta. So thus this is b cos theta. The n dash is equal to n into b cos theta, which happens here. Now the vertical force n on the n dash on the face is released from the static. Will n dash itself on, and sigma sin phi, that distributed for angle of this amount of distributed sin phi into t into b into d phi itself. If we take the integration from 0 to 3, and this will create that downward deflection, and which will be balanced by the force n dash. It will create a downward force here, and it will balance by the force n dash here, which is equal to both together will be equal to the n0 itself. Where n0 n dash, after putting this simplifying this integration itself and adding with the value of n dash, it will become n dash is become minus delta sigma bt cos theta minus 1 minus sigma bt itself. If we so that is equal to sigma bt cos theta. Now if x the phase at section theta is subjected to moment m, the normal force n, which is given by this function itself, and shear force, another shear force V, which is the n sine theta itself, which is equal to, by the same method, n dash is equal to V into Bt cos theta and cos theta sine theta, which is the phase n. So these are the forces we are having act here, other than over this quadrant. So observing that the direction of m is opposite to the one in figure, total strain energy will become alpha v square. Alpha is the coefficient. V is the shear stress L by 2 ng. N is the normal force by 2 AE. M is the bending moment, is 2 AE into E rho 0 and minus M into N, means the bending moment caused due to the action of N itself. So here rho is the radius of central curvature here. This is between here. A is the cross-sectional area. E is the distance between the neutral axis of the curved beam and from the center of the section. Neutral axis of the center of the section. And A is the Young's modulus itself. I know there is no slope across M, no change of slope across Mn. Mn is totally horizontal. There is no slope is changing. Mn is horizontal. Thus, Mn itself is horizontal itself. Just 1 second. So what we want to do is, since there is no change in slope, and there is a horizontal itself, so the rate of change of this energy with the rate of change of this bonding moment m0 acting over it is supposed to be equal to 0 itself. So we are integrating from pi by 0 to pi by 2 and neglecting which is not a function of m0, like this one and this one. We get this portion of the beam and this portion of the beam itself. And if we take the derivation, we will have 2 into n here. This 2 will cancel the 2 in the upper, and so this equation will become m by ae 0 ae a capital E and small e itself, and n by n is calculated here a divided by e, where this rho e is being cancelled while this rho e itself. This rho is being cancelled while this rho itself. So this equation become like this here, dm by dm0 itself. Now substituting for, we can substitute for m and n, which we have calculated like this, just an note. And so what we are doing, we are putting the value of m and putting the value of n multiplied by d theta itself. And as dm by d0, dm0 is equal to 0. So this is all equal to the 0 itself. 1 by e into m0 is half 2 into bc times square equal to sigma bc was squared by theta, which have calculated here. That is, if we have the integration, then if we make the integration now, we'll make m0 equal to theta, sigma bt is all okay, and sine square will follow from convert it into cos 2 theta, then into that will convert into sine 2 theta, theta by, then put the end of integration, boundary of the integration, theta by 0 divided by minus 1 by 4 sine 2 theta. Then sigma bt, again we are following the same process, putting sine square theta is equal to sine, converting sine square theta is equal to sine 2 theta, and that is like this. 2 sine square theta theta 1 plus cos 2 theta is equal to 2 cos square theta minus 1 and cos 2 theta 1 minus 2 sin square theta. So we are just replacing this cos square theta with 1 plus cos 2 theta multiplied by half sin square theta 1 minus cos 2 theta multiplied by half. And we are integrating them, putting it here, both here and here, both cos square theta and sin square theta, and getting this value and make the integration accordingly, because both cases cos theta will be converted into minus sin theta and cos 2 theta is converted into plus cos 2 theta. So here we are getting it plus and here we are getting it minus. Next we are putting the value of and half will placed accordingly, and then putting the value of the boundary condition 0 to pi by 2 and get this value. Ultimately it is to m0 pi by 2 minus half sigma bt ptc divided by pi by 4 multiplied by sigma bt into pi by 4 is equal to 0 itself. Thus m0 is equal to, if m0 is equal to 2 by pi, again half 2 btc by pi by 4 plus e into btc by pi by 4, or sigma bt by 2 into c by 2 plus e. So we are getting value of m0 in terms of between the value of m0 which is being point here in terms of sigma, the external stress, width of the strip b, thickness of the strip t, and c in terms of the thickness of the inner hole itself, and the plus the eccentricity of the centroidal ring to that of the neutral ring itself. Now, the normal stress at the point is, you see, normal stress at the point N, say here. Or here. This is the normal stress at the point here and normal stress at the point here and here. Both are same. Normal stress at the point N of the section is sigma 1 due to the moment m0 and plus sigma 2 due to the longitudinal force n0. So what we are getting, what will be the normal stress at the point is due to the moment there will be a force, there will be a sigma 1, and due to the longitudinal force or vertical force, that will be sigma 2. So since sigma 0 is opposite to that of sigma 1 will, we have already have this calculation in our bending equation, and this equation is being used here, which is actually given by 6.37. That is given by sigma x m by AE minus m by AE multiplied by y by R0 minus y. While m is the induced bending moment in the section, A cross-section area, E is the, that is not capital E but small e, is the eccentricity of the centroid to the neutral axis, and y is the distance of the constant fiber from the neutral axis, and R0 is the distance or radius here, the radius of the neutral axis itself, R0 minus y. So we have calculated m0 here as sigma t here from the earlier equation here, and A cross section area, b minus c multiplied by the thickness t itself, y. Y is the distance of centroidal axis from the central axis, the distance of centroidal axis to the distance of our concerned fiber from the neutral axis itself. Here it is b minus 3 by 2, minus C itself. This is the distance of the centroid. This is the distance of centroid itself. Now, what is do? The R0 is the rho 0, and R0 is the distance of neutral axis to central axis. So central axis given as R0 minus distance is given already given as B E itself, and R0 is B minus C by 2 is the and plus C. So R0 is given by B plus C by 2 minus E itself plus C minus E. So if you substitute all these important values here, and all these values M0, A, Y, R0, etc. in this particular area, and simplify and expressing in terms of radius, will get R1 for this sigma as equal to sigma 1 is the longitudinal force, and sigma 1, and due to the bending force, this is it will be reduced come like this, and sigma 2 is the due to the longitudinal force. This will then come like B by C minus 1. So what will happen? And E, if we plot the E, if we take rho 0 minus E itself, or rho 0 minus E, that is R0, or rho R0, or yes, E is equal to rho 0 minus R0. If we put the value of R0 here, then in these terms, and it will take B plus C by 2 minus B minus C divided by log B by C. So E by C is given by this particular formula itself. If we divide E by the C distance C itself, and here all these C will take this ratio in the ratio form. If let B by C is equal to 5 for a test concentration, B by C is equal to 5 for example. So E by C will 0.1514, sigma 1 0.83 sigma. We don't know the value of external load. Sigma 2 0.25 sigma, and epsilon max sigma 1 plus sigma 2 is equal to 1.83 plus 1.25 into sigma is equal to 3.830 itself. Now this gives the value of sigma 1, sigma 2, and sigma max of several values of B and C. There are several values of the width and divided by the diameter of the internal hole itself. And comparing the values in the table, the exact solution is 3 sigma for a very small hole. It can be seen that for B by sigma between 5 and 8, results of the approximate calculation carry closely with the exact solution itself. Okay. So far, this is this chapter for this time. Thank you yourself. Let us stop our discussion.